In the last lecture, we have discussed the two-step binomial model. In this lecture, we will generalize it to multi-step binomial model using a backward induction technique. Recall the same idea was used in two-step model also. Consider a European option with payoff ht, and let's consider the time discretization Tn is equal to T0, which is equal to 0, T1 to Tn, which is equal to capital T of the option period 0 capital T. We always use the notation Hn instead of Ht in order to have a clear notation for every time step. See, the stock price Sn minus 1, which is only known at the time t equal to Tn minus 1, can be considered as a random variable defined on the probability space with sigma field being Fn minus 1. Remember, the collection of sigma fields Fk is a filtration Fk, right? So once you consider the random variable Sn minus 1 and define the random variable Sn in this way, where u and d are such that 0 less than d less than 1 plus r is less than u. This no arbitrage assumption is always assumed. Remember, Hn, which is the payoff, is a function of Sn, right? See, Sn is nothing but St, that is the stock price at time capital T, right? So you can define Hn like this, where Hnu is max of 0, Sn minus 1 u minus k for call options and 0, k minus Sn minus 1 u for put option. And similarly, you can define Hdn, that is this one. So the payoff is given like this. With these notations, let us proceed to build the backward induction technique. So we just proceed as we have done in the two-step method. The first step of our derivation is the construction of replicating portfolio at the time level t equal to t n minus 1. Remember, we are just taking Hn, the payoff of the option at the expiration, and we have to match it with the portfolio pi n, which is given by phi n, theta n, right? So for that, we first have to get the value of this portfolio at this time. That is, we have to first take Vn, the value of this portfolio at time Tn, that is given by Vn is equal to phi n Bn plus theta n Sn, right? So the replicative portfolio condition therefore gives you phi n Bn I can write as Bn minus 1 into 1 plus r plus theta n Sn I can write as Sn minus 1 u if the stock goes up. In that case, my payoff Hn is defined in terms of Sn minus 1 u. Therefore, I have to write Hn u. This is the notation we have used for the payoff when the stock goes up. And similarly, when the stock goes down, at that time, your replicative portfolio condition similarly can be written as, the first term is the same, the second term is Sn minus 1 d is equal to the corresponding payoff denoted by Hn d, right? So one has to solve this linear system to get phi n and theta n. Since we have assumed no arbitrage condition, you can see that the left-hand side matrix in this linear system is invertible, and therefore we have a unique solution. And the solution of this system is precisely our replicative portfolio given by Pn is equal to U H and D minus DH and U divided by Bn minus 1 plus R into U minus D, and theta n is HU n minus HDN divided by Sn minus 1 U minus D. So we obtained the replicative portfolio at time level Tn minus 1. As a next step, we will use the self-financing condition, which is also one of the assumptions that we made on our trading strategy. So what it says is that the money that you use to set up the portfolio pi n, what is the money that you have spent to set up the portfolio pi n? It is nothing but the value of pi n at Tn minus 1. Remember, this is different from the value of the portfolio, which is defined as V of pi n at Tn, right? So this is the amount that you spend in order to own this portfolio. This should be equal to Vn minus 1. What is Vn minus 1? Vn minus 1 is the value of the previous time step portfolio, pi n minus 1. At Tn minus 2, you would have set up that portfolio's value at Tn minus 1, right? That is Vn minus 1. So the self-finance condition says that Vn minus 1 should be equal to V pi n into Tn minus 1, okay? But what is V pi n Tn minus 1? That is equal to the same thing, but the price is at Tn minus 1. Therefore, it is Vn Bn minus 1 plus theta n Sn minus 1, right? So that is the self-finance condition. Now you see, we have phi n expression and theta n expression. You can put both of them and you can see that this can be written as 1 by 1 plus R into HNU P star plus HND 1 minus P star. What is P star? P star is the risk neutral probability given by 1 plus R minus D by U minus D, right? So what we got now is an expression for Vn minus 1. Remember, your Vn minus 1 is the value of the portfolio constructed at Tn minus 2, right? We have not explicitly calculated pi n minus 1, which is at Tn minus 2, but we got the value of this portfolio at Tn minus 1 without knowing what is pi n minus 1. How we got? We got that information from the portfolio constructed at Tn minus 1, which is pi n itself, okay, using the self-financing condition. So just recall, if you take n is equal to 1, then we have V naught here, right? And that is what we have taken as the price of the option in the one-step model, right? So similarly, what we will do here is we will assume that the payoff or the value of the option at time Tn minus 1 is equal to Vn minus 1. So what is Vn minus 1? Vn minus 1 is the value of the portfolio pi n minus 1. Okay, so we assume that the options value is equal to the value of the portfolio pi n minus 1. Why it is so? Well, the proof of this theorem goes exactly how we have done the pricing theorem in one-step method. We have proved it fully in the class. So the same idea goes with this also. You can take this as theta n minus 1 bn minus 1 plus, sorry, this is phi, and theta n minus 1 sn minus 1. Okay, this is the actual definition of Vn minus 1 that you take as Hn, which is the price that you will pay for the option at the time Tn minus. Then, since the market is no arbitrage market, you can assume that if this condition violates, that is, if Hn minus 1 is less than this quantity, then you can construct a arbitrage portfolio. Similarly, if Hn minus 1 is greater than this quantity, then also you can construct a arbitrage portfolio. With that, you will conclude that you can take Hn minus 1, that is the price of the option at t equal to Tn minus 1, as precisely Vn minus 1, which is given by this, and that in fact can be written in this form using the self-financing condition, right? So therefore, with this theorem, you can in fact write the option value at t equal to Tn minus 1 is equal to 1 by 1 plus r into Hn u p star plus Hn d 1 minus p star. So that is the option price at t equal to Tn minus 1. Just observe that we have not done anything new now than what we have done in the one-step method. It's exactly one-step method. We have just followed and got the value of the option one time level before the expiration, right? So now we will take Hn minus 1 as payoff at Tn minus 1 and do the same process to get the value of the option at Tn minus 2. And like that, we will keep on going backward till we reach the time level t equal to T naught, at which we get H naught, and we declare that that is the price of the option at t equal to T naught. That's the idea. Let's go further backward and see what is happening. Before going to the next step, let us give an important remark. Look at this quantity. This quantity is nothing but the expectation of Hn. So if you also include that, then it is Hn star. And since it is based on the risk neutral probability, we generally denote it by E star, right? So this is the expectation of Hn star, and you observe that this itself is a random variable. Why? Because Hnu and Hnd, they themselves are random variables defined on the space S and Fn minus 1. So this is more precisely a Fn minus 1 measurable random variable. And further, one can also show that it is nothing but the conditional expectation of Hn given Fn minus 1. Therefore, we use the notation E Hn star given Fn minus 1 for this expression. Since Hn star is written, we will also include this discount factor here. So with this notation, we can write Hn minus 1 as E star of Hn star given Fn minus 1. Let us now move on to the last step, that is backward induction. Remember, we have started from the last step Tn, and we have constructed the replicative portfolio pi n at Tn minus 1 using the payoff Hn and obtained the value of the option at Tn minus 1, which is denoted by Hn minus 1. So we have this in hand. Now the same idea, whatever we did to get this Hn minus from Hn, the same idea now we will do for the level Tk minus 1 given the value Hk at Tk. Okay, so you keep Hk in hand and try to find the value of the option at Tk minus 1, which is defined by Hk minus 1. The idea is exactly the same. For every k equal to n, we have already done n and obtained for n minus 1. Now we are just generalizing it to any k. Since we are going backward, I am writing k equal to n minus 1 up to n. We assume that we have the fk minus 1 measurable random variable hk. That is, we assume that we have this random variable and we have to construct or we have to obtain the random variable hn minus 1. How we do is, first you use hk to construct a replicative portfolio by k at the time level t is equal to tk minus 1. See, we don't need to do all these steps explicitly, again, because we know how they look like and how the solution of the linear system will look like, and then everything we know. So therefore, it just for the sake of completeness, I'm just writing the steps. We don't need to do them explicitly. Then impose the self-finance condition and you will obtain Vk minus 1. That is the value of the portfolio pi k minus 1, which was built at Tk minus 2, that you will find the value at Tk minus 1. So that you don't need to explicitly construct this, because you can obtain this using the self-finance condition as we did in the nth case, and that gives us Vk minus 1. And then you will have finally that no arbitrage theorem we can use to define hk minus 1 equal to vk minus 1, and it is given by exactly the same expression as we got, because there is no change in these steps. Only thing is, instead of n we have to put k, the index, that's all. Otherwise all the other expressions remain the same, and we get hk minus 1 is equal to that expression, which we will write in this notation, given fk minus 1. So you repeat this step for each k until k is equal to 1. At k is equal to 1, we have, so when you put k is equal to 1 in this expression, you have h naught. You have h naught, which is equal to E star of h1 star given f naught, but you don't need to write f naught, because remember, f naught is the trivial sigma field p and s. Okay, therefore there is really no information given to us. Therefore you don't need to write this. You simply write Ex of h1. Remember, it depends on s naught, and s naught is not a random variable. Therefore, this will be a constant and will not be a random variable. Therefore, that also one interpretation for why we don't write the conditional expectation here. Well, this is the required option price for us. Let us find the explicit formula for this. So for this, let us use the following notation. Remember, at the time tk, your stock price is denoted by sk, and that can be obtained from s naught by going up some j number of times and down remaining, that is n minus j number of times, right? So that we will include in our subscript and write like that, where j can be 0, in which case your stock from t equal to 0 went only downwards. When j equal to 1, it means somewhere it went once up, remaining all were down. Similarly 2, 3 and so on up to n. When j equal to n, it means the stock price went only up in every time period. So with this notation, we will denote our hk. Remember, hk is a function of sk, and that we will now write it as j, and therefore we will have this hk which corresponds to skj as hkj. You can just write few examples and see. For instance, your time period t naught, if you take s naught and then s naught u, and similarly at time step t equal to t2, you have 4 different cases and so on. So you can see that this is S1 comma 1, and this is S1 comma 0. This is S2 comma 2. This is S2 comma 1. This is also S2 comma 1. Note that these two are numerically the same value, and this is S2 comma 0 and so on. So the next level will be here S naught u u u, that will be S3 comma 3, and this is S naught u u d, that is S3 comma 2 and so on, right? And the corresponding HK, the payoffs at that time level, will be denoted by whichever triggers, whichever SK comes out at that time level. With respect to that, you will be calculating the payoff, and therefore you will be denoting it by this notation. So this is a notation we will use and obtain an explicit formula for this quantity, and therefore for our option price, more importantly. That is our aim. Let us see how to do that. Remember, H naught is nothing but E star of H1 star. This is by definition H1 up, therefore it is 1. Star we will put because there is a 1 by 1 plus R factor is there. And since 1, that is U, is there, therefore its probability is P star plus H1 comma down is there, therefore it is 0, and that denominator 1 plus R factor is there, therefore you have a star there. And since it is down, therefore the probability is 1 minus P star. So I will remove this star and write it like this: H11 P star plus H10 1 minus P star. Now the question is, what is H11 and what is H10? Remember, H1 is given by E star of H2 star given F1. That is nothing but 1 by 1 plus R into H2 up. That is in our old notation, it is H2U U P star plus H2D 1 minus P star, right? Now we have two possibilities, H11, it means in the first time level we went up, right? Therefore, H11 should have these two possibilities, that is 1 by 1 plus R into H2. So H22, which corresponds to this value, H22, that is when it was success, therefore you have P star plus H corresponding to 21, that is this term. So H21, that is down, therefore 1 minus P star. And similarly, H10, it means you have gone down in the first time level, and therefore you have these two possibilities. When you have used S21, it means the stock went up, therefore you have H21 P star. Well, there is a 1 by R factor here, that is equal to 1 by 1 plus R into plus H2 0 1 minus P star. Okay, so let's put these two into this equation, and we get H naught is equal to 1 by 1 plus R the whole square into H22 P star plus H21 1 minus P star, everything multiplied by P star, plus H21 P star plus H20 1 minus P star, again everything multiplied by 1 minus P star, that we can write as 1 by 1 plus R the whole square into H22 P star square plus, there are 2 times H21 P star into 1 minus P star plus H20 1 minus P star the whole square. The next step is to go to the time level 3. For that, we note that H22 can be written as, by our formula, E star of H3 star given F2, right? So since it is H22, it is given by the random variable S22. That is given by H33 star P star plus H32 star 1 minus P star. Similarly, the other stuffs, H21 is given by E star of H3 star given F2. Here it is coming from S random variable S21, and that is going to be H32 star P star plus H31 star 1 minus P star. And similarly, H20 is given by E star H3 star given S20, which is equal to H31 star P star plus H30 star 1 minus P star. So putting all these values above and noting that H3 star can be written as 1 by 1 plus R, we have 1 by 1 plus R, already square is there. Now one more 1 by 1 plus R will come out, that will make it cube, and you have H33 P star plus H32 1 minus P star the whole P star square plus the second term 2 times H32 no star because we have removed 1 plus R already out, therefore it's only H32 P star plus H31 1 minus P star times P star into 1 minus P star plus the last term H31 P star plus H30 1 minus P star into 1 minus P star the whole square. So everything together you can write as 1 by 1 plus R the whole cube into H H33 P star cube plus 3 times H32 1 minus P star into P star square plus 3 times H31 1 minus P star square P star plus H30 1 minus P star the whole cube. So this is in fact the formula for three-step method. So we can go on like this. Here itself you could have seen the pattern that is forming up, right? So you can generalize it, and we get the formula for H naught in the n step, which we will write in the form of a theorem. So you are given an option with period 0t, and it is partitioned into n subintervals. It means you have n time levels in the partition of the time interval. The price of the attainable European option, it means an option for which we can develop a replicative portfolio, and you are doing it in a no arbitrage market, then you can get a unique price for that option, and the price is given by this formula. You can see that at each level you get this kind of pattern. Therefore, in general, you have this formula, and this is the formula for n-step binomial model. Note, once you have this formula, you don't need to really have all those technical things that we have used in deriving this formula. All those technicalities are purely for deriving this formula. But once you have this formula, it's very easy. You give me R, you give me U, you give me D, you give me S naught, and of course that this needs the strike price K also. And R, remember, is the per period interest rate. Okay. If it is given annually, then you have to carefully convert it into per period and then apply it here. Okay, so once if you are given all this, you can obtain the option price without getting into any technicalities like filtration or conditional expectation or replicative portfolio or self-financing condition. Nothing is needed. You just have final formula. This formula is also called CRR formula, which C stands for Cox, and R, the first R stands for Ross, and the second R stands for Robinstein. They wrote a very famous book on option pricing, which is considered to be one of the earliest books in this subject. And they basically developed this model. Their version, if you see, it's just a little bit complicated, but finally it means this formula only. So from the examination point of view, I may give all these parameters and ask you to find the option price. Also, I may ask you to find replicative portfolio, although it is not explicitly used in finding the option price, but it is there behind the screen for deriving this formula. Therefore, I may just ask you to also find the replicative portfolio and so on. Okay. So therefore, you just have to know how to create them.